Deep Learning Tutorial by Simplilearn. My name is Richard Kirschner with the Simplilearn team, and today we're going over the Deep Learning Tutorial. What's in it for you? We're going to cover what is deep learning, what is neural network, what is a perceptron, how a neural network works, backpropagation, cost function, types of neural networks, and then we'll get into a demo using Python and build a neural network. What is deep learning? Deep learning is a type of machine learning that works on the basis of functionalities of human brain. It trains machines to work on vast volumes of structured and unstructured data. Deep learning uses the concept of neural networks that is derived from the structure of a human brain. And if you've ever seen images of a human brain network, you have dendrites, inputs. You have cell, which is a nucleus, as your nodes. You have synapses, which create weights, and an axon, which create an output. Now, this is a very simplified version of the human brain. And there are certain sets of cells that are strung together very similar to how today's neural networks perform. But they still have a long ways to go, and the human brain is still significantly more complex with hundreds of different kinds of cells and different interactions that we don't see yet. So what is deep learning? Artificial intelligence. So you have your AI is a method of building smart machines that are capable to think like human and mimic their actions. Be careful with that definition. We're a long way from a human cyborg coming in and taking over. When we talk about this, we're usually talking about automating single kind of instances or things going on. How do we automate a new process? How do we automate a small robot to do something? How do we get a drone to fly out and when it loses contact to turn around and come back in the direction it came from? Those are very simple processes and significantly lower than the scale of like what human thinking does. Now, a subcategory of artificial intelligence is machine learning. Machine learning is an application of AI that allows machines to automatically learn and improve with experience. There's a lot of tools out there to use with machine learning. And you'll see linear regression models and things like that. They're much more common when dealing with straight numbers, a linear regression model. And there's other models that just do basic math functions quite well. But then we get into one of the subcategories, deep learning. Deep learning is a subfield of machine learning that is used to extract patterns from data using neural networks. And again, we're talking about complicated patterns. When we talk about image processing and things like that, they're not as straightforward as the numbers in stock exchange. So you start looking at another way to solve these problems and figure out, is that a raccoon in the picture or something? Much more complicated.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
Deep learning performance. So when we talk about performance of deep learning and the amount of data, the performance goes up. The more data you have, the higher the performance. When we talk about a lot of machine learning platforms, they kind of peak out at a lower level. So again, you can think of this as having thousands of pictures of raccoons, like I said before, versus the numbers in a stock exchange, which are very rigid and very clear. You have a close and an open in the stock exchange kind of thing. Where when you have an image of a raccoon, the color shading, all kinds of things go into trying to figure out, is it a raccoon? So when we look at what is a neural network, and we really look into kind of a nice image of it, today's neural networks usually have a layer of inputs, and you'll see here we have input 1, 2, and 3 with x1, x2, x3. So you have your input layer, you have your hidden layers. This might have multiple layers depending on what you're working on. Then you have your output layer, which in this case we have two outputs, y1 and y2. And you can also see the connectivity here. So everything in the first row connects with everything in the second row in the hidden layer. And if you had another hidden layer, everything in the first hidden layer would connect to the second hidden layer, and then everything in the second hidden layer would connect to each of the outputs. And then they'd make calculations based on that. And this is interesting because there's so many different aspects of neural networks nowadays that are changing this basic configuration. They find that if you skip a hidden layer or two with your input going through, that actually changes the results and works better in some cases. There's also convolutional neural networks, which look at windows and adding up the numbers in them. There's a lot of complexity when we start getting into the different aspects of what you can do and how you build neural networks. And again, it's very much in an infant stage, so this basic diagram does a great job of capturing what it looks like now. The input layer is responsible to accept the inputs in various formats. The hidden layers, again there's that S, could be multiple layers, is responsible for extracting features and hidden patterns from the data. And patterns and features is important. We want to look at features. You usually talk about features as your input. You have input 1 is one feature, input 2 is another feature. If you're looking at the iris data, it might be the width and length of the petal. Each one of those would be a feature. You have these nodes which generate a number that doesn't really have a specific representation, but it becomes a way of looking at it, adding the features together and creating an importance value there. And the output layer produces the desired output after completing the entire processing of the data. What is a perceptron? A perceptron is a binary classification algorithm proposed by Frank Rosenblatt. And you'll see here we have our constants come in our inputs. We have a constant 1 for the bias. The bias is important. You can go back to Euclidean geometry where you have a line y equals mx plus b, b being the y-intercept. That's what that constant is there needs to be some kind of adjustment that basically is the y-intercept. And you have your inputs, you have your weights, you have your weighted sum, your activation function, and an output of 0 or 1. And so here we have, we'll go ahead and walk through these. We have x1, x2, x3 are the inputs. W0, W1, W2, W3 are the weights. Weights are values that determine the strength of the connection between two neurons. And if we go back to this slide, let me just flash back here to this slide, you can see how each one of these nodes has multiple inputs. So when you look at the hidden layer of the outputs, they have multiple inputs. So each one of these nodes has these inputs. They might be the original features coming in. They might be the layer of nodes before. And so you have your x1, x2, and x3 are the input into your node. Your weights are the weighted values that determine the strength of the connection between two neurons. The input neurons are multiplied with the weights, and a bias is added. There's that 1, which is weighted, the y-intercept in Euclidean geometry, to give the resulted weight sum. The activation function applies a step to check if the output of the weighting function is greater than 0 or not. There's a lot of ways to do an activation function, but this is the most common, or the most, not common, but the most easy to see way of doing an activation on here. So we look at, here we go, walking back through this diagram and taking a closer look at it. We have the predicted output is compared with the actual output. So once you go through the step and it adds everything together in there, and these are your weights are multiplied, they're just multiples. So you have feature of x1 times weight of 1 plus feature of x2 times weight of 2, so on, plus the weight times the bias. And we go ahead and compute all those all the way through. The node comes out and we have the actual output, and then we go ahead and have a predicted output. What do we think it's going to be? And this is on each node. So keep in mind we're zero in on the node. This isn't the whole process because this actually goes through all the nodes, but there's another step in here when we get to that part. The error in the network is estimated using the cost function, and backpropagation technique is used to improve the performance. So when we look at the in the backpropagation algorithm, the cost function is minimalized by changing weights and biases in the network. And you can see here we have our input layer, we have our hidden layers, and we have our output layer. And so you could think of this as we have our actual output. We predict what it's going to be. In this case we have two outputs. We might predict that it's either nothing there or a raccoon. So one of them comes up and says, I don't see any kind of animal, and the other one says, this is a raccoon. So it's either yes or no. And if it gets it wrong, it says, that's wrong, and it sends that error back. And that error goes through the first set of weights, which then go to the hidden layers and their set of weights, which goes back to B1, the other layer, and their set of weights. And it adjusts those weights as it goes backwards. and it says, hey, this is the error on the output. We kind of adjust it a little bit. The part that we don't adjust in the first set of weights, we say, there's still an error, so we send it to the second set of weights and so forth. What happens is as we adjust these weights, each one of these nodes starts creating kind of a category or something to look for in whatever image or data we have going in. And so for making a better predictions, a number of epochs are executed, where the error is determined by the cost function. Now, epoch is an important thing to keep track of. Epochs is if you have a large, or any data set, and let's say you've split out your test date and your training data set and you're running your data through, how many times do you have to run all of that data through before you start getting something that is usable, till the error goes down to, you can't adjust the error anymore. It's the lowest error you can get. So each time you go through a full set of data, before you repeat and go through the same data, that's called an epoch. The error is backward propagated until a sufficiently small error is achieved. And again, that's what we're talking about. We're trying to minimize the error. So we get to a point where that error really isn't changing anymore. You just have the same error coming out. And there's other ways to weight that error too. The cost function or loss function measures the accuracy of the network. The cost function tries to penalize the network when it makes errors. And you can see here we have a formula for the cost function. C equals 1/2 of the y predicted minus the y, the actual y, squared. And of course the squared value removes the sign because we don't know whether it's plus or minus when you look at an error. And then the C, this is your cost function. How much is it going to cost? How much of an error do we really have that we're sending back? And so we have, with the cost function, we can look at this, we can look at it as a loss, and the epoch, again, that's every time we go through the data, that's an epoch. How many epoch runs are we going to go? And so we have a nice graph here that shows like a very high learning rate, low learning rate. Different data is going to change depending on what you're working on. They put the yellow as a good learning rate because it has a nice slope to it, and you think, yeah, the more epochs I go in, the lower the loss. So that means you're going in a good direction there. And as you curves down, it gets to the best answer, has the lowest loss on there. So looking at types of neural networks, we have the GAN, we have the DBN, the RBFN, the autoencoder, the RNN, the LSTM. This is a flash of some of the main ones that are out there. There are now so many variations that there's variations on the variations. And so just quickly jumping into these, you can see we have a number of them here listed. And these are just like a flash of some of the more common ones, like the GAN, General Adversarial Network, where you have two different models competing against each other until they find which one can beat the other one. Kind of think of a chess game where you keep flipping who's in charge. And then we might look at the DBN, which is a deep belief network. And they're used to recognize clusters and generate image video sequences generally. And we have the RBF network, or RBFN, which is your radial basis function network, which uses a different set of activation functions to figure out which is the right weights. Autoencoder. The autoencoder is a little different than the other ones in that it looks for an error, but the error is based in finding data that groups together. So it's a way of sorting the data out without knowing the answer. That's what an autoencoder does. RNN has a couple different definitions. Most of the time you now see it as a recurrent neural network, where the output, part of the output goes back into the input. So they call it, that's what's recurrent. There's also another RNN which deals with learning step by step as opposed to over a set of data and weighting it as you go. And there's the LSTM, or long short-term memory recurrent neural network. It's also an RNN which deals with how do you sort something like a sentence out where the last word depends on what the first word was, and so it slowly weights things as it goes through to figure out what's being said. Again, these are just a quick flash, and even as I was describing them, you should have been like, well, why don't you hook an autoencoder into a GAN and then run that with a DBN? Well, there are tools to go ahead and mix and match these things. So you will actually see when you start doing layers, you might have the layers of one type of neural network feed into the next neural network, and that's actually pretty common. And we talk about deep learning libraries. There's a lot of different things out there, but the big ones that they usually talk about, and most of these are dealing with larger data, is like TensorFlow, Keras. Keras and TensorFlow play nice with each other, and Keras kind of is usually integrated with TensorFlow. Caffe, Theno, PyTorch, DL4J. These are all different deep learning libraries, and there's many more out there. There's a Scikit has a deep learning library in it under Python. Scala has one that they've been building on there. So these aren't the only ones. TensorFlow is probably the most robust one at this time, but that's not to say the other ones aren't catching up and there's not all kinds of other stuff out there. Now, going through and talking about these things is all fun, but until you get to roll up your sleeves and take a look at the code and see what's going on, it's really hard to see what we're talking about. So we're going to go ahead and do a deep learning demo on text classification. Now, to do this, there's a lot of different editors you can use for Python. Currently my favorite's always one I'm currently using, which changes from month to month or year to year depending what projects we're doing. We want to look at Anaconda Navigator, which does a nice job building your different packages and environments, and go into Jupyter Notebook. And so we'll go into Jupyter Notebook and create our setup in there to run a neural network. And so we open up our Jupyter, we'll go ahead and create a new Python 3. And let me just bring this out to the top. There we go. So now we would have our Jupyter 3, and I like to always give it a setup on here. So this is the text classification we're doing today. We'll go ahead and rename that. And we were talking about, if you remember from the beginning of the thing, I said some of one of the most robust packages out there right now is TensorFlow, along with Keras, which usually works nicely with TensorFlow. So we're going to go ahead and be working with the TensorFlow and the Keras. We want to go ahead and do a number of imports in here. This is just set up on this. A lot of this really isn't necessary for what we're going to do. There's different things we can do. So we're going to go ahead and from future, we're going to import absolute import, division, print function. These really don't do a lot other than they help us kind of display things later on. You don't really need them. You can just do some basic print on this if you want to. So I'm not going to dig too deeply into that setup. But we do want to take a look at iteration tools, because we're always iterating over things. Again, you don't really need the iteration tools because a lot of TensorFlow will do this for you. But it's a lot of times when we're building these packages, we don't think about it. We just bring in all our tools that we might need. The big ones, though, is our Pandas DB. And let me switch to a draw thing. It's always nice to kind of maybe give us arrows here. There we go. So when we're looking at, you can see here, here's our Pandas. Pandas sits on top of NumPy, our number array. Pandas is our data frame, just makes it really easy to bring in the data, view the data, and kind of work with the file. That's what these two are for. And of course our matplot library up here is for displaying it. And then we have the sklearn. These are for doing metrics and pre-processing. Some of this you can actually pull off of TensorFlow. I tend to bounce back and forth between the sklearn setup. And by the way, the sklearn has its own neural network, a real simplified one compared to what TensorFlow does. But we want to go ahead and do this in TensorFlow, where we're going to be using TensorFlow Keras. And Keras is nice because it sits on top of TensorFlow, but it's easier to use. It's a little bit like you could think of TensorFlow as being the back end, which you can program in, and Keras being a higher level language, which makes it easier to do things in. And you can see here we went ahead and printed out TF version. We're using TensorFlow as the back end, and you have the TensorFlow version 2.1.0. Always important to double check your versions. You never know what's not going to work with what version of Python and so forth. So it's important to check those. This is Python 3.6. I don't know if TensorFlow is fully integrated with 3.7 or 3.8 yet. I'm sure if it isn't, it soon will be. And so we're going to go ahead and bring some data in. This is consumercomplaints.csv. And if you want a copy of this file just for your own to play with, you can put a note, send a note to Simplilearn, and they'll be happy to send you a copy of that. And then DF stands for data frame. That's very common, and we're using the pandas to go ahead and read this comma separated variable file in. And we'll go ahead and print what they call the head. If you've never worked with data frames, usually when you see head, it means the first 5 rows of that data frame. So you can see what's going on in there. And give it just a moment to read that in. There it goes. And you'll see in here that we have a date received, a product, mortgage, credit reporting, consumer loan, credit card, subproduct, other mortgage, NAN, NAN, whatever that means, whatever, it's just missing data right there. There's nothing in there. Vehicle loan and so forth. And then, of course, different columns. And this is a data frame. Data frame has rows and columns. And a lot of times when you're processing data frames, you can think of mapping, map and reduce as a terminology. We're mapping. We're either mapping each of the rows, like you might be running a process on each row, or you're running a process on each column. And then one of the most common things would be, say, to sum parts of the row together and have a total value of cost, or maybe sum the total. You might come over here, wherever, I'm sure there's a value in here. Complaint ID, they don't actually have a value. But it'd be something you would process by column. You might want to find out how many different companies are listed here. So that might be something you'd run on the column. So that gives you an idea. We have our data frame, DF head on there. And if you remember, we're looking at text classification. So that makes sense that we don't have any dollar values in there. And we're going to look at just a couple of these columns. Certainly you can do this with a number of different objects on here, but we're going to take just the columns consumer complaint narrative and the product column. And in this case, when we handle null values, there's a lot of different ways to handle null values. But in this case, we're just going to go ahead and do just the not null. We only want those that are not null in the consumer complaint narrative. And let's go ahead and print that, do the DF head. In Jupyter, the last line, if you just have a variable, it automatically prints it out. So you could put print and put brackets around DF head and it'd do the same thing. And you can see here we have our consumer complaint narrative. I have outdated information on my credit report, and then you have your credit reporting and so forth on each one of these. An account on my credit card was mistaken. The company refuses to provide me verification. The complaint regards to square to something. So we're going to be looking at these complaint narratives and trying to understand them. And can we write a code to optimize that? And then one of the things we always do, like up here you'll see where we already removed the null values. I would go ahead and just double check, sum up the null values. Are there any null values in our data frame? And this is just a simple way of looking at every cell. This includes consumer complaint, the product, and so forth. And you can see here we have 0 null values, so that's good. We're not going to play with the null values today. And then we can also go ahead and take a look at our end aspect we might be looking for, which is our product. We have credit reporting, consumer loan, credit reporting, debt collection, debt collection. Let's go ahead and just take a look at this and see how many counts we have. And you can see here that there is, under debt collection, 47,000 entries. Under mortgage, there's 36,000 entries. Under credit card, we have over 18,000 entries. So this is a pretty big database. And you can see it going down all the way down here with the different entries that go underneath of product. So we have, and one of the things we don't spend a lot of time on in some of these demos is what is really defining what we're looking for. Now, if you're doing a data science project, you usually start by exploring the data and then you define what you're really looking for. And so we're kind of skipping through that particular process. It does constitute a small amount of time, but as far as the importance, it's one of the most important things you can do in data science is ask the right questions. So even though you're spending 80% of the time cleaning data, building your models and everything, that 20% of asking the right questions has a higher impact. And so you really should be making sure that you understand what the questions are. That's domain knowledge. So we're talking, in this case, banking. And so in this case, it might be that as consumer complaint comes in, we can start looking at these consumer complaints and what product they're attached to and what that means. We're not going to dig too much into the domain and asking the question, what exactly are we looking for. We really want to look into the process as far as building a neural network. And so the first thing we want to do is go ahead and split our data. We need a train set and a test set. The train size, in this case, we're going to do 80% of the data is going to be for training our neural network. And then we'll go ahead and use we'll switch that over for the test size to be the 20%. Let me go ahead and run that. And you can see here, train size has 159,000 entries, and then we'll test that on, we've held out roughly 40,000 of those entries for our test size. And then for this example, we're just going to split it. The first part of the data will be for training our data, and the second part will be for testing our data. So we're not really doing a random setup in here, which is okay because this is an example. A lot of times you might split this. One of the things I do with neural networks is I will split it into 3 sections, and I will test 2 as training and the third as the test. This is obviously not big data. You don't want to do this on something that might take days to process. And then I flip it, and then so I'll run it 3 times, and those 3 times will give me a nice narrative of how good my model is, and then I'll actually run the final product on all 3 sections to program it, to train it. So it gives me a good basis of what kind of error I have versus, on test models, while having a very robust model to publish. In this case, though, we're just going to go ahead and split it based on the first part goes to the train and the second part goes to the test. So one of the next things, whenever we deal with text, and this is such an important line, I want to go ahead and just highlight the tokenize. You'll see the word tokenize, tokenizer, setting it up. We're taking the words and putting them into a format the computer can understand. There is a lot of ways to tokenize words. In some cases, you call them 0, 1, 2, 3, 4. Depending on what you're doing, it might just be a 0 or 1. So when we talk about the encoder, we're usually talking about, as far as tokenize, we actually are looking at, in this particular case, we'll be looking at each word as its own feature. So when we looked up here, remember right up here, let's see, here we go, money transfer. Let me go back up just a note here. Turn that off so I can go back up. If you remember up here, we have this right here, consumer complaint narrative. So I would be a feature, have would be a feature, outdated would be a feature, information would be a feature, on feature, my feature, credit feature, report. And you think, wow, that's a lot of features. Yes. In running through bills put out by the United States that are being voted on in the government, it comes out roughly 2.4 million different words are used in those bills. That's a lot of features. And so we're going to go ahead and look at max words, tokenize, and tokenizing words. There's a lot that is happening here in the tokenize setup. And so we'll go ahead and let me just put together some of this code here. So the tokenize is an actual object in here, text tokenizer, and it has number of words equals max words. So we're going to limit it to 1,000 words. Character level equals false. Fit on text train narrative, only fit on the training data. And so this is kind of interesting because it drops a lot of these words. Why would it drop a word? Well, on is probably used a bunch and really doesn't have any value. So that would be one of the words they'll probably drop. And it also, there's other things it can do, like it can also combine combinations of word. It might be that this company, this complaint, these might be always together. So at some point it might actually bundle some of these words as a single feature. There's a lot of things that go into that. We're not going to go into too much detail because you really have to go through the API on these to understand all the different encoding and setups you have. This is just a really fast way to do this, and it works. I like easy and I like things that work. I don't know about you, but when I'm running through and doing a lot of different models, I might start tweaking these once I have an answer, but until then, we want to go ahead and run the encoder and do something simple like this. And so using sklearn utility to convert the label strings to number index. And so here's our encoder, label encoder, encoder fit. And this is sklearn, of course, everything's fit. And then we do ytrain equals the encoder transform train product, ytest equals encoder transform test product. Now, what's going on here, now up here we did the X, where we have, let me view up here, where we were looking at, here we go. I have outdated information on my credit card report. Now we're looking at this, credit reporting, consumer loan, credit reporting. And if you remember, this is our list of those, debt collection, here's our list of them. They're not a huge number. And so we're going to encode these differently. This is just 0, 1, 2, 3, 4, and so on. Not necessarily in that order, by the way. So be a little careful on order. So we're going to convert the labels to one hot representation is our next step. And that's what this is doing. So we have our number classes npmax ytrain plus 1. Our ytrain equals utilities to categorical. So here's where we're taking our y value in the training set, and we do the same with the test set. And we go ahead and run that. So now we've created a ytrain and a ytest where we've numbered our categorical, we've created categorical data so it's easy to read the answer and translate it back. And we've encoded up here our X, and we used a tokenizer. So a little different. Encoder puts in 0, 1, 2, 3 for the different listings. An encoder or token, you can get tongue-tied on these. A tokenizer takes and creates a huge, in this case we've limited it to 1,000 words. Each word is its own token. And to really see what we're looking at, let me go ahead and we're going to inspect the elements and see what we ended up with. Let me run this. And so we have our ytrain shape. There's our 1,000. Where does that 1,000? Maximum words. So we've tokenized the top 1,000 words as each as its own feature. And the same thing with the X test. So those are X train and X test. We have our ytrain shape and our ytrain test shape. And I thought the encoder, depending on how you set it, either does 0, 1, 2, 3, or in this case it actually puts it out as 18. So it did the same thing as a tokenizer as far as putting it as a 0, 1. So you have 18 choices there. And if we count these, I'm guessing there's 18 there. Now, this is the part which is, when we look at the encoders and the tokenizers, these are the tools you need to process text. The computer doesn't see the hello on. You have to give it a 0 or 1 in each one of those. And so this is all about the text classification part. This is how we classify text, is we have to give it something that has a number representation. So once we've sorted out our data and we've converted it into something the computer can read for doing text, we want to go ahead and create our model. And when we create our model, one of the things to be aware of is this is what we call a black box model. Now, they've come a long ways in understanding how these different processes are created, and so they're starting to understand how you can put these together and go back and say why. Why does it pick this? Why does it pick that? How does it balance that? But it's black box in that it's really hard to do. It's really hard to go in there and figure out why it picks one over the other just by looking at the neural network itself. There are other machine learning tools like decision tree which make it much easier to see those changes in how it branches down, but they don't perform as well in many cases. And so we're going to go ahead and build a model. We'll go ahead and run this just because it builds the model, doesn't actually start fitting it yet. Let's take a look at these different pieces. So we have our model, which is going to be sequential. That's a Keras, so we imported that at the beginning from the Keras setup. This tells us what's going on, that we're going to be running this from top to bottom. And we're going to add a dense layer. So each time you see add, we look at these add, each one of these, we're adding a row. So these are all rows. And then of course our rows. You're like, what is a row? So we talk about row, these are your layers. We have, you can see right there, input layer. We're going to add an activation to this layer, and we're going to use the ReLU activation. Then we're going to add a dropout rate. And what this does is they found that when they process a neural network, instead of processing every neuron each time you do the backpropagation to train it, you only process some of them. So only some of them are being trained. By doing that, it's able to create the differentiation between different categories, and it actually trains much better instead of trying to train them all at once. So that's what this is right here with the dropout 0.5. And then we add dense number classes, and the dense number classes is another layer. So up here we have our add and activation ReLU layer. So we have our input, our ReLU layer with a dropout of 0.5. Then we have a dense layer which uses a soft max activation. There is a lot going on with Keras and these models. You can get lost in just the activation. Here's our two activation. ReLU is one type of activation. Softmax is another. They work differently. And you can see when we were talking about earlier, when we talked about the different kinds of neural networks, in Keras and TensorFlow, each of those layers can be a different neural network layer and can function differently. And you can stack them on top of each other and feed them into each other. And then the final thing, of course, is your compile. We have what we're using for loss. Remember, we want to minimize loss. So category, this is a type of way of minimizing that loss. Atom is an optimizer. You'll find there's a number of optimizer. Atom is used for larger data sets. As you get to smaller data sets, you actually use a very different optimizer in here. And we look at the accuracy. That's just when do we stop compiling this data? How far do we go until it starts building what they call a bias? It's overfitted. We want to stop at the right moment. And then finally we get to actually training our model. This is that black box. We're going to fit it to the data. We don't know what's actually going on in there, but we want to go ahead and run it. And I'm going to go ahead and start it running because it takes a moment for it to run through, and you'll see the epic feed down here as it goes through epic 1 of 5 and so forth. We'll freeze this just for a second. There we go. So let's take a look at this. We have batch size. Batch size, oops, I meant to do that in an arrow. There we go. Batch size is how many rows of data we're going to feed at a time. So you can feed larger rows. There's different reasons to feed them at different sizes. Really, a lot of times people just leave this as a default, depending, and let it choose for them. I'm not sure why they picked 32 in this case. There's probably, when they were messing with this, 32 probably was a good batch size for fitting it. The back-end math deals with differential equations and some calculus, which we won't get into. So being aware of that this batch size affects how it does that back-end differential equation in the reverse propagation, tells us that this is actually a pretty important number. If you get it too big, it's not going to fit as well, and if you get it too small, it takes way too long to process. And a lot of times there's what they call a reinforced learning neural network where it's batch size of 1. What does that mean? Well, that means every action you take has a feedback. You program the neural network so you can guess what your next action is. That's very common, like in trying to beat video games with a automated setup in a neural network. The epoch says we're going to go through all the data in the training set 5 times. So that's what this, remember we talked about epochs? That's what the epoch is. And we can see when I let it go out here, we're on epoch 2.5. So we'll go ahead and pause this. I'm going to go ahead and pause it for a second, let it finish running. Or while we're waiting, we can actually take a look at some of this data here and see what it's actually generating for us. And so when we look at this, accuracy, loss. So we want to minimize loss. The metrics is accuracy, and you can see that we're going to want the accuracy to go up, and we want the loss to go down. And the loss is going to be what we want to minimize. And this is just some of the metrics. And it talks about like value loss, value accuracy, and how they're changing with each time we run it. And so you get to a point where it no longer gets better or worse, and at that point you really want to stop running it. You can overfit it. And overfit it means it's going to miss some of the generalities that you need when solving some of these solutions. And then I didn't talk too much about what's actually going on here. What are we doing in the domain of this particular one, which it looks like it is trying to figure out based on a consumer complaint narrative. Maybe they send in a complaint. What product is it connected to? So maybe they get the complaints before the product or something like that. I'm not sure why you do this particular setup. That would be, again, a domain knowledge in here. So what we're doing is we're using the consumer complaint narrative to predict what product they're talking about. If someone sends in an email and says, I have outdated information on my credit report, they're probably talking about a credit card reporting. If you get a random email that says, I purchased a new car on blank, the car something something, probably a loan. That's what we're trying to do, is if you get a random input from the consumer complaint narrative, you can point to the product that they're referring to without having to call them up and ask them, I guess. It might be useful, not sure. Now that we've gone through all 5 epochs, let's go ahead and evaluate the accuracy of our trained model. And so we have, we're going to go ahead and do a score for the model.evaluate, a nice Keras setup where we can do the X test and the Y test, the batch size, verbose, and then it's going to generate a score. And one of the things, let's just go ahead and print so you can see why they broke out the score. Let me just go ahead and print the score in here. Let's go ahead and run that. And so it's testing the score. It's going to take it a moment to go through all the data. And it gives us a nice score. It says the test accuracy. These can mean a lot of different things, but we have a 0.5. To be honest, without looking at the data, I would have to look and see exactly which things it missed on and how it scored on there. But it's getting about half of it. It's able to pull in half of it and say, hey, if this is the complaint, this is what it's connected to. Keep in mind when we're talking about text, that's really good. Can you imagine some of this stuff? I don't know if you've ever worked in tech support or IT or at a counter in the mall or even in taking orders someplace as a waiter or waitress or fast food or whatever. When you try to understand people, it gets pretty crazy. So even an accuracy score like this is probably pretty good for understanding some of this text, and there might be steps you could do to improve that. And so let's go ahead and go through here and look at actually using it. And we'll punch this in. It says how to generate prediction on individual examples. We have our text labels in our encoder class. And we'll just go through a prediction equals model predict NP array of X test of I. Predict label, text labels, prediction, print test narrative, so forth. And this is just, let's go ahead and run it because reading through print statements can be very painful sometimes unless you actually see what's going on. So when the president came out with the HARP program, ... the actual label was mortgage, the predicted label was mortgage. So when this person sent this complaint in, maybe you don't know what it's connected to yet, you can guess it's probably a mortgage. I filed a dispute with Capital One Bank on ... and it says, oh, credit card. Well, it turns out it's actually debt collection is what it predicted. So yeah, missed a little bit. A lot of times when you dispute something, it probably is debt collection. In this case, it was specific to a credit card. Okay, so we missed that one. I am disputing account number XXS with Midland, whatever. Actual test label debt collection was debt collection. I opened a Barclay card on to help rebuild my credit card, mortgage, so forth. We can go through all of these, and you can see it does a pretty good job. It gets close, or in fact, most of these it pulled in correctly, credit card reporting. And this is a lot of what we talk about with text setup. Sentiment's a really big one. There's a whole sentimental libraries out there, whether someone is positive or negative towards something. If you're pulling off Twitter feeds, you might want to look that up. You might want to look at connection towards postings in, what was it? There was running stock. I actually do some stock programming code, so I end up coming back to that a lot. Finding sentiment feeds on different stock value and different stocks out there on out of national publications really helps trying to predict what the stock's going to do. What are people going to do in buying and selling stock? Same thing with this. We can now predict their complaints and try to figure out what it is they're complaining about. Now that wraps up our deep learning demo on text classification and gives you a nice introduction to deep learning as opposed to shallow learning. Bad joke on my part. But you can see how a deep learning model can go in and do a lot of things that you might not be able to do using basic linear regression or many of the other machine learning models. And text classification is one of those where neural networks really shine because they can pick up things that you can't really measure in other ways. Thank you for joining us today at Simplilearn. For more information, please visit www.simplilearn.com. Get certified, get ahead.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.